hello, it's nice to see you all here. My name is Semjon, and I want to present some things I found when I researched into mobile ID for my graduation thesis. And I want to take you on this journey to see all the findings that I've got. So, mobile ID, what is it? It's an Estonian digital identity solution. It means that you can authenticate to e-services and also sign files online. And to be honest, that's a kind of old solution. It was released way back in 2007, and it's maintained by ASK ID Solutions. Now, for using mobile ID, you need a SIM card, and it should have a special application installed on it. And this special mobile ID application, sadly, is closed source. SK would not give it to us, sadly, so we cannot really see what's inside. Now, when you take this SIM card and put it into your phone, you are ready to use mobile ID to authenticate and sign files. And both of the things actually work in a very similar manner, using transactions. So let me show you how a transaction looks like. So you have some e-service on the right, for example, your bank, and imagine you want to log into it. So you enter your data, click enter, and then a mobile ID pop-up appears on your phone. In this pop-up, you can see some information about the transaction, like the verification code, what the e-service started the transaction, and also a description of it. So you click OK, you enter your mobile ID PIN code, click OK one more time, and that's it. The bank is now convinced that you are indeed you, and the transaction is completed. So what actually happened was that the bank had calculated some hash that it wanted to be signed. Then this hash somehow got into your SIM card. The SIM card had created a cryptographic signature over this hash, and then the signature got back to the e-service. So mobile ID had undergone some changes in all the years it was here. One is that they added the support for elliptic curve cryptography, so you can actually have mobile ID with elliptic curve key. And as far as I know, it's the only used possibility right now. So they deprecated RSA, and some time ago they had also deprecated the RSA certificates. They had actually revoked some of them, and they had introduced a new API for e-services to call the mobile ID backend. Oh, I mean connect. However, in all this scheme, there's one part that I believe had never been changed. That is the communication scheme between the mobile ID backend and the SIM card. And what I find notable here is that no comprehensible description of the scheme has ever been published. So I took it as a challenge, and I tried to document the scheme as much as I could. And to a large extent, the work was successful in this regard. So, how the transaction actually works. It all starts when supposedly the user wants to make a transaction, connects to the relying party, and expresses that they want to do a transaction. The relying party then calculates the hash, it creates a description of the transaction, and connects to the mobile ID backend and sends this information to the backend. The backend then communicates with the OTE server, over-the-air server. So this server is kind of like a configuration server for a mobile provider. So for instance, if they want to push some updates to the SIM cards, they will use this server and send some SMS messages. Now, when the server gets this information, it creates an SMS message, sends it to the phone, and as any SMS, it's actually sent in exactly the same way, using SMS sender. When the phone gets this message, it will actually not show it to the user, but relay it to the SIM card. And when it is done, the SIM card, the phone then communicate, so the user could see the pop-up. I will show you in a moment how it is done. And then the SIM card creates the signature, creates an SMS with this signature, delivers it to the phone sends it to the OTA server, it in turn communicates the signature back to the mobile ID backend, also called the TSP platform. And then the TSP platform returns the signature to the e-service. And so the relying party had got the signature, and the transaction was successful. So you can see communication channels here in different colors. The first one, from the relying party to this TSP platform, it's a well-known API. You can find it on the GitHub, I mean the documentation for it, and it's just TLS. Then what happens between the TSP platform and the OTA server, sadly we can only guess. Then the message, the SMS message is delivered in a usual way, so nothing too much mobile ID specific here. However, this last part is what interested me the most. What happens between the phone and the SIM card? How this pop-up message actually appears on your phone? So I got curious into this and researched this part a little bit more. Yeah, so how would I do that? The SIM card is supposed to be inside the phone. How would I observe this communication? Sounds difficult, but actually there is a specialized device for it, thankfully. It's called SIM trace, and here it's how it works. So I took my SIM card from my phone, inserted it into this device, and then I hooked up my phone to this device using a PSB cable, some sort of cable. Now I need to flash a special firmware to this device. It's called SIM trace trace defu. And now what happens is that I can monitor the communication between the SIM card inside this device and the phone. And I can actually see this communication or sniff it if I use a special application on my laptop. It's called SIM trace 2 sniff. And after the setup is done, I can just use Wireshark and see this communication. Now, what I found. First of all, the general structure of this communication. The phone and the SIM card. The first thing to know here is that the SIM card is actually a smart card, just like your ID card in this regard. And this communication follows command response logic. So the phone sends a command to your SIM card, the SIM card performs the command and gives the response back to the phone. Now, there is a special standard defined to help developers of SIM card applications to have some extra functionality. For example, to make a message appear on the phone, or send a message, or maybe ask for some input. And these features are defined in this standard right here. So one of the features is that the phone can now send some information to the SIM card. Not an instruction, just some information inside an envelope command. For example, this could be an SMS message with the hash, for example. And the other feature is that SIM card may ask the phone to perform some commands. So how it works? It's slightly complicated, but nothing too bad. So the phone sends some command to the SIM card. It's completely unrelated to what the SIM card tries to do here. And the SIM card actually responds with a code notifying that it actually has a proactive command ready, so an instruction for the phone. The phone then supposedly fetches this instruction from the SIM card, and the SIM card communicates this instruction back to the phone. Now the phone supposedly performs this instruction, completes it, and then the result should travel back to the SIM card. And then the SIM card may either say that there are no more instructions, or that it wants to perform some other instruction on the phone. Let's now see how it actually works in Mobile ID. So here you can see the general scheme. First of all, when the phone gets this message with the hash, it communicates it to the SIM card using envelope command, the command that I mentioned. Then the SIM card asks the phone to play tone. When the tone is played, the phone communicates the info back to the SIM card, and the SIM card asks the phone to notify the user of the transaction using display text command. And that's the exact same prompt that we've seen before. Now, when the user clicks OK, the SIM card will be notified about it and ask the phone to show this prompt where a user should enter some data. In this case, it's PIN code. Now, one funny thing about this prompt is that you can actually see there's a star sign, hash sign, and plus sign present. That is because you can actually type them in. And you can actually have these symbols present in your Mobile ID PIN codes. Another funny thing is that all this communication, it is not encrypted, and there is no mutual authentication, which means that you can actually read the PIN codes right from the Wireshark. Or you could have some other device that sniffs communication between those two, and then you can see it too. Now, let's zoom in on this message that comes to the SIM card and see what's inside. So it starts as any other SMS message with a header that is standardized. And the most interesting thing about this header is this PID and DCS fields. They tell what type of message it is. And in this case, this type is close to message with raw data. So these fields is how the phone knows that it should actually forward this to the SIM card and not display it to the user. Also, you can see the origin of the message. And those digits spell out 95544. This is the OTA server for Elisa mobile provider or mobile operator. And here's the remainder of the message. I found out that it actually matches the format described in this standard, and it's called the secured packet. So the first thing to note here is this tar field. It says which applet on the SIM card should get this message. And in this case, it is PKI. So that's an identifier for the mobile ID applet on the SIM card. And then the SPI field. It's very important because it tells which security features are enabled for this message. And in case of mobile ID, it's encrypted with 3DS, and also it has a counter and a checksum. So according to the standard, these are the fields that must be present inside the encrypted part. So the encounter and checksum are actually inside it, so I cannot even see what those values are. And the secured data, those are the values that are specific for mobile ID. They are encrypted and we cannot see inside. So sadly, no luck here. We do not really know the alignment of the fields inside this portion of the message. However, we can make some good guesses. Let's take another look at this mobile ID prompt. The first thing you can see here is that the Reliant party name is clearly visible. This means it must have come with this message. Then it's the text of the transaction. In this case, it's login to internet bank. And also its format, because there are two different formats and they support different characters that can be displayed. Then it's the language of the prompt. Look up here and you will see verification code string. And it can be actually localized. So if the prompt is in English, then it will be verification code. It can be different for Estonian and Russian languages. Then the type of the transaction is obviously present, because the user knows whenever they are authenticating or signing some file. And then obviously the transaction hash. Now, when I performed my research, I found out that there is another field, which I call hex identifier, and it basically identifies a mobile ID transaction. So it kind of maps the incoming message with the outgoing message. And on the next slide, we'll see more about this. And another thing, please see this verification code, this 4-digit code that is displayed. We cannot really know for sure whenever it is calculated inside the SIM card from the hash or included in the message. And this is a very important question. That is because the mobile operator has all the keys it needs to actually read and modify this data inside the incoming SMS. This means that they can actually substitute the display text, so the text of the prompt that is supplied. They can modify their own party name, and they can even tamper with the hash. And this is extremely important because we don't want the user to sign something that they didn't intend to sign. And if the control code is present inside the message, that means that the OTA server can just substitute the hash and get a signature on something else. And there is even an attack if control code is not present in the message. There is still an attack, but I won't disclose this attack to you. Now, let's see what's inside the outgoing mobile ID message. This is the outgoing message in all its entirety. And first things first, we notice the type. It's, again, class2 message with the raw data. The values here are slightly different. That is because this message is not intended to be forwarded to the SIM card, because, well, it originates from the SIM card. After that, we see the origin, and it's the address of the OTA server again. And this message is not encrypted, so we can actually see inside and know what's encoded in there. So first we see the header, and throughout all my experiments, these values stayed the same. So I believe this notifies the OTA server that this is actually a mobile ID SMS and not some other configuration SMS, for instance. Then it's the type, and this value has changed. So whenever there is a signature inside this SMS, the type will be 00, so a successful transaction. It can be some other value in case the user canceled the transaction or there was some error inside the SIM card. And then this hex identifier. We can actually see that it's in clear text here now. And that's why I believe that it was included in the incoming message. So there are 8 bytes, and they spell out 8 ASCII characters. And those 8 ASCII characters are, in fact, hexadecimal. And after that comes the encoded signature. In this case, it's elliptic curve signature. So the setup I mentioned before with the SIM trace device, it's great for sniffing data. However, it would be really cool for performing the experiments And to see more about Mobile-ID, if I could actually tamper with the data and change it, so change the SMS that goes into the SIM card and change the SMS that will be sent to the OTA server. So there is a new setup for it. And the focal point of this picture is this phone on the top. It's called Motorola C115. And the special thing about this phone is that it is fully programmable. So I can receive and send from it any data that I want. It runs layer 1 firmware. And to control this phone, I need an application called layer 2.3 that must be running on my laptop. Then remember I mentioned that the SIM card is actually a smart card. That's why I can just put it inside the smart card reader, hook up this to my computer, and it will work. Well, not right away. I need to use another component to make the phone and the SIM card friends with each other, so to say. So the phone would actually use the SIM card to authenticate to the mobile network and to receive SMS messages. Well, it would be great, but the layer 2.3 application is not that smart. It doesn't support SDK communication that is needed to perform Mobile-ID transactions. So I needed an extra component, some Python code. And with all that set, I'm ready to conduct experiments. Now, the experiments themselves are somewhat complicated, so I'll only share the results with you. First of all is that the secured packet that comes with the incoming Mobile-ID message, it is actually secured. So the counter appears to be working correctly. The checksum seems to actually be checked. And it seems that the information, the secure data, is actually encrypted with the key that is specific for some SIM card. However, other fields that you can see in pink here, they are not verified. This means that I can tamper with the timestamp, with the fields that say the type of the message, and even with the origin of the message. And SIM card will still get those messages, and it will be able to perform Mobile-ID transaction. So even if I send Mobile-ID message from some other phone number somehow, then it still will be accepted. And the resulting Mobile-ID message, so outgoing message, it still will be correct, in the sense that we'll still have the correct origin. I found out that I can actually send secured packets to the SIM card that for which all the security features are disabled. So no encryption, no checksum, and no counter. And that's really cool because it potentially opens possibilities for communicating with the SIM card and issuing some commands to it. However, I still could not make my own Mobile-ID messages, incoming Mobile-ID messages, because I sadly do not really know the format, what's inside the secured data of the secured packet. And also another thing that I found is that you can actually send those service messages, at least within the LSAE network and perhaps some other networks. I did not pursue that path further, but I'm sure some of you hackers will actually figure out some creative and annoying ways to use this feature. Now, I tampered with the outgoing messages too, and here you can see the format once again. And I learned that the signature is validated by the TSP platform before it is sent to the relying party. So in no case, relying party should get a signature that is not valid. This will not happen. And this causes relying parties to be dependent on the TSP platform in needless ways. So if you are a relying party, please check the signature anyways. The signature can be tampered with, and the signature format can also be tampered with. So whenever I did that, I found out that one of the three things could happen. First is that the transaction will just complete successfully. Some fields aren't actually checked in this signature format. They are not that important for the security of the scheme. Then it may be that the TSP platform reports an error to the relying party. That is, if the signature itself is invalid, then the error will be communicated. And the same works if some part of the format was tampered with. And then another thing is that may take place is that the OTA server will just ignore this message, and the signature will never get back to the TSP platform. And one such case is that if I modify the hex identifier, the OTA server will disregard this message because there is no transaction with a hex identifier that I supplied instead of the original one. And also, the OTA server ignores messages that are sent from the wrong phone numbers. So this is a nice feature. And that's pretty much all that I wanted to share with you. And now I urge you to ask questions, please.
user question, slightly outside the scope. When I receive the in-1 or the authentication message, sometimes my phone makes one beep, sometimes two sequential beeps. From Wireshark, is it always the same message that is sent to from the SIM card to the phone that now?
That is somewhat weird. I hadn't noticed that the command changes at all. What I did notice is that how this command is designed is kind of loose for implementators on the phone. So what kind of beep is there? It's actually defined by the phone manufacturer. So it's not like hardly specified. Yes, of course. Question, yes.
You have a question? Yes. So during the testing, you were interacting with both like telcos and government infrastructure. Any kind of legal implications that might arise from that?
From this study?
Of this testing, yes. You were basically like sending messages. You inform them?
I guess there's no legal implications because I didn't use any systems without authorization. And of course, we could run our own e-service, and in this case, there are even no questions at all. And to be honest, the only thing that e-service sees is that whenever there is some actual signature supplied back, or there's some kind of error, so the e-services are not concerned at all, to be honest.
Yes, of course. Could you explain more about this Motorola phone? What's exactly programmable there?
Yeah, so to be short, some schematics, as far as I know, had leaked out. And this allowed some hackers, so to say, to find out how to use this phone to send messages. It's only that. It's not only the firmware of the phone, like menus of the phone. It's actually the component that is actually responsible for this wireless communication. So in this sense, it's fully cracked open, and that's why it's useful. Yes?
Can you explain what exactly you mean by sending messages? Because you can send messages with a phone. That's kind of functionality.
Oh yes.
What is the typical SMS level, I guess? Like you were talking about level 2 SMS.
Yeah, let's see this message again. So when you actually send a usual message, then those fields, PID and DCS, I think they will be zeros if it is a usual text message, or some other value in any case. And usually, of course, your phones do not allow you to send service messages, because they are supposed to be service messages sent only by machines, so to say. But in that phone, it's very easy to send whatever message I want, including the one with the values for service messages.
I have a question.
Yes, of course.
You said that the incoming message is encrypted with 3DS. Is it breakable? I think 3DS is not hardware proof for the encryption. Or have you looked into that?
I heard that there's some research into how we break these applications in practice, but I hadn't really researched whether it is viable in this case or not. What I do know is that if I remember correctly, there were 2 keys used in 3DS. So one of the keys actually repeated, if this has any security considerations to it.
There's a question there.
I have a question about how much of the text or prompt displayed to the user on the phone is actually controlled by the relying party. Can one relying party spoof its identity as another one?
Yes, great question. So the Mobile-ID backend will filter any requests to it if the relying party name is not what it is supposed to be. Yes, please. No. Okay. Any more questions, please? Yes, of course.
As a user listening to this, do you have an opinion of is this kind of ID more secure than, for example, smart ID or some other methods?
Well, ID card is for sure more secure, and I'm not really sure about what will be the relation between the mobile ID and the smart ID, but I for sure know that this scheme has significant disadvantages. For instance, that the OTA server can substitute the hash. I believe this to be an important issue. Something to keep in mind for people who design future protocols.
if I got it right, you mentioned that the communication between the SIM card and the phone itself is unencrypted, which is why you could have just sniffed it with Wireshark. Does that also mean that, for example, if you had like a malicious app installed on the phone, it would also be able to check all that data?
I'm not sure. Maybe if the phone is rooted, then perhaps it is possible, because there is some part of the phone that actually communicates with the SIM card. What I do know is that if you could manufacture some very thin SIM card and put it in between the actual phone and the SIM card, then the SIM card will have access to all the communication. And you can actually, I don't know, figure out a way to communicate with this thin SIM card in between your phone and the SIM card from the outside. So there may be an attack where you first sniff the PIN code, and then you remotely say to this thin SIM card, oh, please send the PIN code now back. Or even the next transaction that will come, please accept it. So there are different attacks that take advantage of this.
There's a length field in the envelope. Have you tried like messing with it and changing it and seeing if that makes it behave differently, or?
Whenever I tried to tamper with the structure too much, the SIM card just notified me that it had no proactive commands ready for the phone. So if I mess up with the length fields, then usually what happens is that the SIM card just refuses to do anything in terms of mobile ID transaction. You had a question?
I just had a short question, like, is there any theoretical way that the OTA provider could spoof your signature towards the provider?
What do you mean by spoof? Just substitute?
Like instead of you getting the SMS and sending the request back, would it be a possibility somehow that, for example, Elisa will say that, okay, you signed this like request and you actually haven't entered your PIN code.
Oh.
Is there any way for them to be the man in the middle and like kind of?
It's not that bad. So the signature that is created inside the SIM card, the cryptographic sound protocols are used. So Elisa cannot just create a signature for you, because the keys are inside the SIM card and they are supposed to never leave the SIM card.
Are the SIMs unique enough?
Yes, you can actually be convinced in that because you have mobile-ID certificates, and you can see that for different mobile-ID certificates there are actually different public keys. And so because of that, you know that the private keys should be also different.
But can you remind how does this private key get into the SIM card, which I get from the mobile operator?
Yes, so whenever the SIM card is manufactured, then somewhere in this manufacturing and personalization process, those keys are getting flashed inside the SIM card. So this personalization process is kind of closed, and it is disappointed for me, because I cannot really be convinced that this key is not copied somewhere else.
So then potentially your attack scenario kind of can be done.
So it could be potentially the same Gemalto case technically. If it's a
Keys generated outside the card.
Yeah, if they generate outside of the card. Yeah. We have more questions in the back. Yeah, Anko?
You mentioned that the applet code of the SIM card is closed source. Yes. If you leave aside the secret keys for a moment, why do you suppose it's closed source, and should it be like this?
Sorry, I hadn't heard that.
Why do you have an opinion on why the applet code is closed source and not available for the public?
Well, there may be reasons why SKI wants to keep it secret. There may be some legal obligations, but I honestly think that this is a bad practice, and this applet code should actually be published. Maybe if they have some significant faults in it, maybe they should have undergone some public review process in this sense. So there may be reasons, but I don't think it is a good enough excuse. Same for mobile ID applet code. ID card applet code.
Follow-up question. Do you know who actually wrote the source code? Like, is it SK, is it the Estonian government? Who should I talk to and pressure them to publish it?
I'm not sure Estonian government took a large part of it. I do not remember the names of the people, and honestly, I don't really remember that. But I guess SK took some part of it, of course.
like how does the applet code get on the SIM card? Is it like provided by SK to the chip, like SIM card manufacturer, and they like put it into the code, or is it done at the? It's not done at the operator. Like how does the applet code get onto the SIM card?
Well, I believe it is either. I think it is the personalization stage of the process.
Okay.
Any more questions? Okay, it seems silent, so thank you. You can see my graduation thesis if you'd like to know more, or ask me some questions. Feel free to just approach me.